Alright, complex loci. So earlier in the year we started with algebra, we moved into conics equations. So slicing a cone from various angles or eccentricity and getting four different geometric interpretations of that cross section. We're now going to just take that idea and we're going to now do that in the complex plane. And some really interesting stuff comes out. So before we get started, we're going to just take our time and we're just going to go through a conics review. Just make sure that we understand all of our basic conics properties, if you will. So the first thing we went through in conics is the parabola. So it's given by the equation y minus q all squared is equal to 4a times x minus p. So that's just a pq shift. Okay, so this is the locus of a point which moves so that its perpendicular distance from a fixed line, the directrix, x equals p minus a, is equal to its distance from a fixed point, the focus. For this one, it will be found at a plus p, q. That would be the coordinate of that focus. Okay. Then we learnt about the circle. So x minus p all squared plus y minus q all squared is equal to r squared. And the definition of the circle is it is a locus of a point that moves, so there's always a fixed distance, radius r, away from a fixed point, the centre, pq. It's a nice easy one. Then we've got the ellipse. Now the ellipse is in the form x minus p all squared over a squared plus y minus q squared over b squared equals 1. And its definition, if you recall, is the locus of a point which moves so the sum of its distances from 2 points, the foci, is constant. And so the foci for this is at p plus or minus a squared minus b squared all square rooted q. So that's basically just p plus or minus c, isn't it? That distance from the centre to the focal points. But we want it written in terms of a and b. So p plus or minus the square root of a squared minus b squared q. That is the coordinate for the foci, and it's got a constant distance sum to those 2 points is 2a. Hyperbola is very similar, basically just changes the signs. So hyperbola, x minus p all squared over a squared minus y minus q all squared over b squared equals 1. And it is the locus of a point which moves so that the difference between its distances from 2 fixed points, the foci, is constant, plus or minus 2a. So p plus or minus the square root of a squared plus b squared q, that is the focal points, and the difference between its distance to those 2 focal points is constant at plus or minus 2a. Plus 2a giving one branch of the hyperbola, minus 2a giving the other branch of the hyperbola. So that's a bit of conics review. I've got one extra little conics review bit that I want to show you as well. It's quite important for complex loci, and that is, just cover up the diagram for it, that is a perpendicular bisector. It actually has a bit of a conics definition as well. Pretty simple. It's the locus of a point which moves so that it's equidistant from each endpoint. So what I've drawn here, if I can pick this piece of paper up, is we've got this line and we want a perpendicular bisector. Well, this dotted line is perpendicular bisector of this line here is equal distance to both points. So this is the pathway that a point would make, so there's always equal distance to these two. So I've drawn I've drawn 3 isosceles triangles on here, showing that that's always going to be equal distance to those 2 endpoints. So that's another nice bit of information for us going forward. So before we get stuck into the complex loci, we're just going to have to, we reviewed conics, we're just going to need to review how complex numbers link to vectors. So, complex numbers link to vectors. So a complex number, so a variable complex number, z, is written x plus iy. And we can view this as a vector, xy, with a real component and an imaginary component. Now when we're working with vectors, all we really want is their size and their direction. So if I've got these two vectors, u and v, well, what happens when I add u and v together? So what we can do is we can take u and we're just going to add the size and direction of v onto that. So the size of v is, for this one, is 2 centimeters at that approximate angle. So that is going to be u plus v. I'll draw that in red. So u plus v looks like this. This red vector is u plus v. Now we could go v plus u as well. That would be the same thing, because we would take v and would add on this 3 centimeter vector at that same direction, and that would give us u plus v as well, v plus u. Now when we're adding vectors, we add them head to tail, and this is the parallelogram rule, because as you can see, it makes a parallelogram. So u plus v is the same as v plus u. So that's how we add vectors. And it's very similar if we're subtracting vectors. So u and we're subtracting v, that will be the same as u plus negative v. So negative v would be in the opposite direction. Negative v would be there. That's negative v. And if we added that onto u, we'll take that negative vector and we'll just add that on like so. And then our new vector would be here, u minus v. So that is how that vector addition and subtraction work. Couple other little points to point out is if we have u as a vector u1, u2, then we know that the absolute, or the length of u, the modulus of u, is given by u1 squared plus u2 squared, all square rooted. So just a bit of Pythagoras. So that's just the same as the modulus of the complex number as usual. And if we wanted, so if we wanted u minus v, if we wanted the size of that, well, that would be the, so modulus of u minus v, that would be u1 minus v1 all squared plus u2 minus v2 all squared, and that would be all square rooted. So just be the difference in the real parts squared and the difference in the imaginary parts squared, all square rooted. So basically z minus w, absolute value or modulus, this basically just represents the distance between two complex numbers. And that's basically it. That's it for review. So what we're going to do now is complex loci equations. So let's get rid of these. Let's bring in a fresh piece of paper. And the first complex loci we're going to do is going to be the parabola. So you could pause the video, have a quick read of that again if you can. But now we're going to go through and look at what it means in the complex plane. So parabola is the locus of a point removed so that its perpendicular distance from a fixed line is equal to its distance from a fixed point. So perpendicular distance of z from the directrix x equals what was it, p minus a. I've got some notes with me so I try not to make too many mistakes. So that's just basically the real part of z minus p minus a. And we know from a previous video that the real part of z is z plus z modulus, conjugate, sorry, z conjugate over 2 minus p minus a. And distance between z and the focus, which was a plus pq, well, that's given by z minus, from a previous video, a plus p plus qi, and it has to be an absolute value because it is a distance, and so the complex locus of a parabola is then just this part here, the perpendicular distance to the directrix, so the real part minus p minus a, so z plus z conjugate over 2 minus p minus a is equal to absolute value of z minus a plus p plus qi. That there is our final equation for the complex locus for a parabola. So the real part of z minus p minus a, that gives you the distance to the directrix, and we want this to be equal to the distance of z to the focus, a plus pq. And obviously the q is an imaginary part of the axis or plane, so it's qi, and it's the difference between that, but we want the absolute distance as well, so we're going back to that distance formula. So that's it for the parabola. That is the complex locus for a parabola. Okay, the next one is the circle, which is a bit easier. The parabola is a wee bit to get your head around actually. So you can pause the video, have a read of that just to remind yourself. So the circle is a locus of a point that moves, so there's always a fixed distance away from a fixed point. Okay, so distance from z to the center pq, how can we write that? Well, that's just given by z minus p plus qi, because that is p, there's a vector p plus qi in the complex plane. So that's the distance z to the center, and this should be equal to some fixed distance, r. So that's all we have to do, is make that equal r. And that is our complex loci for a circle. Really easy. Okay, let's get rid of that one. Let's bring in a fresh sheet and let's do the ellipse. So here is the ellipse review from conics. So a locus of a point which moves, so the sum of its distances from 2 points is constant. So we're basically going to have two absolute value things added together equal to some constant value, because that is the definition of the ellipse. So z and the positive focus, so the distance from z, our variable complex number, to the positive focus is given as z minus p plus a squared minus b squared square rooted plus qi. That is the distance from z to the positive focus. And the negative focus to the negative focus is just z minus p minus a squared minus b squared square rooted plus qi. So it's just changing that sign there. And so when we add those together, it should be constant at 2a. So we're just going to add these together. Z minus p plus a squared minus b squared square rooted plus qi. That's the positive focus, written like our vector notation, plus z minus p minus a squared minus b squared square rooted plus qi equals 2a. So that there is our complex loci for the ellipse. Cool. So if you ever see an equation, say z minus 2 plus 3i plus z, I don't know, minus 2 minus 3i is equal to 5, you're going to know that that is an ellipse. Okay? Alright, hyperbola. So, hyperbola review from the conics part of this video. The locus of a point which moves, so its difference between its distances from two fixed points is constant. So it's just going to be just like the ellipse. So let's go distance from z to positive focus, and then we're going to get the distance from z to the negative focus. So first one is obviously just going to be absolute value z minus the positive focus, so p plus a squared plus b squared square rooted plus q. That is our first distance to our positive focus, and then just going to change that sign there. Z minus p minus a squared plus b squared all square rooted plus qi, which I forgot there. And that is our distance to negative focus. And it's not the sum of these two distances that equals plus or minus 2a, but it is the difference between these two. So we are going to write this as z minus p plus a squared plus b squared square rooted plus qi, absolute value of that, that's the distance, minus z minus p minus a squared plus b squared square rooted plus qi, and that's going to be equal to plus or minus 2a to give both branches of the hyperbola. And that is our equation for the complex locus for a hyperbola. Okay, last one. The perpendicular bisector. Should be pretty standard. I'm just going to make this point here AB. I'm going to make this point here CD. And we're going to just derive the complex locus. So perpendicular bisector of a line joining two fixed endpoints. The locus of a point which moves so it's equal distance from each point, A, B, C, D. So we want the distance, so if this is Z, this is the path that Z can take. We want the distance Z to CD and Z to AB to be the same. Well, the distance Z to AB in the complex plane, that's just Z minus A plus BI. We want that distance. The distance from Z to CD is just Z minus C plus DI. And we want just the distance. And we want those distances to be the same or equal. So that there is how you derive the complex locus for the perpendicular bisector. Cool. Hopefully that makes sense. I might do a couple of examples of those at a later date.